in the last few sessions we defined the outer measure, we saw some properties of it, and we defined what are measurable sets. So, this is these are called Lebesgue measurable sets. The collection of Lebesgue measurable sets is what we were looking at. We proved that it is a sigma algebra, meaning the empty set and the whole space Rn are Lebesgue sets. That is a trivial assertion. We proved that it is closed under countable unions and complements. Thus, L of Rn, the Lebesgue sets form a sigma algebra, and we restrict the outer measure, which is defined on the power set of Rn, to this sub collection, which is the Lebesgue sets. We will prove that it is actually a measure. That means, we have to prove that it is countably additive, restricted to Lebesgue sigma algebra. Okay. So, we take countably many disjoint sets from the Lebesgue sigma algebra and prove that it is the outer measure restricted to Lebesgue sigma algebra is actually additive. So, let us start. So, we will start with an observation. So, observation, this is a trivial observation which we will use soon. So, so we have this collection of sets L of Rn. So, take some set measurable. So, this will belong to L of Rn. So, by definition we have for every epsilon positive an open set O will depend on epsilon such that, so what we have is an open set such that the outer measure of O minus E is less than epsilon, and of course, E should be contained in O. Okay. So, we can approximate E nicely from above using open sets. Well, this is same as saying we can approximate E from inside by closed sets. So, let us see why. Okay. So, E belongs to L of Rn. L of Rn is a sigma algebra, this is the Lebesgue sigma algebra. So, E complement will also be measurable. Okay. And so, by definition there exists, so given epsilon positive, there exists some open set. So, let us call that G, an open set such that E complement is contained in G and measure the outer measure of G minus E complement, this is less than epsilon. Well, what is G minus epsilon? So, G minus E to the E complement, this is same as G intersection E complement whole complement, that is the definition of course, which is G intersection E, because E complement is E, which is equal to E intersection G complement whole complement, right. So, I am just writing trivial set theoretic operations here. So, recall that E complement is contained in G. So, E complement is contained in G, and so if I take G complement, that will be contained in E, and G complement will be a closed set, right, because G is open. So, G complement is closed. Well, now coming back to this equality, we have this is equal to E minus G complement, right, that is the definition. And we know that the outer measure of the left hand side is less than epsilon. So, we will get after measure of this is less than epsilon. So, m star of, so let us say hence m star of E minus G complement is less than epsilon, and this is a closed set. Okay. So, that is just rewriting the definition of measurability. Okay. So, instead of this you can say that there is a closed set contained in E such that, so let me write this as a statement So, this is same as, so what we want to say is E is measurable implies, in fact it is equivalent to, but let us not worry about it, implies there exists F contained in E. So, you are approximating E from inside, F closed such that the outer measure of E minus F, F is inside E, right, is less than epsilon. So, well, implies for every epsilon positive there exists a F closed such that from inside you can approximate E by closed sets. So, this is an easy observation, we will use that. So, next aim is to prove that outer measure restricted to, so aim is to prove that M star restricted to the Lebesgue sigma algebra. So, we denoted this by M, remember that this is the Lebesgue measure. Lebesgue measure is countably additive. Okay. So, actually a genuine measure, that is the theorem we want to say. So, let me write this as a theorem. So, this will complete the construction of the Lebesgue measure. So, if E1, E2, E3 etc., they all belong to L of Rn, that means they are all measurable, disjoint, okay, then the measure adds up, right, that is precisely what we want to prove. So, measure of union Ej, j equal to 1 to infinity, this is summation j equal to 1 to infinity m of Ej. Okay. So, that is precisely the countable additivity of the Lebesgue measure. So, proof. Okay. So, we will use the earlier observation. Okay. So, first, so there are two cases. So, A, first assume that Ej, the sets we are looking at are bounded. Okay. Ej are bounded. So, union Ej need not be bounded. Okay. So, it is just the Ej's, the components which are bounded. Okay. Now, given epsilon positive, well, before that let us use subadditivity. So, in general, so forget about Ej's are bounded or not, we have by subadditivity M of union Ej. So, this is the measure of Ej's, right, union Ej. Well, this by definition is M star, right, M star of the union Ej. This by subadditivity is less than or equal to summation j equal to 1 to infinity M star of Ej, which is of course summation j equal to 1 to infinity M of Ej, right, because these are all measurable. So, each time when I write M, it is actually M star, but the set would be a Lebesgue set, right, that is the only difference. So, we have one way inequality, that union the left hand side is less than or equal to the right hand side. So, one way inequality is there. So, LHS is less than or equal to the RHS. So, that is true. So, we need to prove only the other way inequality to prove that they are same. Okay. So, let us start. First assume that Ej are bounded. Okay. Then by the earlier observation, given epsilon positive, we have closed sets, right. You can approximate the measurable sets by closed sets. We have closed sets Fj. Well, what are the properties of Fj? Fj are closed and is contained in Ej, and the measure of the difference will be very small. So, M star of Ej minus Fj is less than epsilon by 2 to the j. Okay. So, epsilon by 2 to the j you have seen earlier these kind of arguments, because we have countably many sets, we start with epsilon by 2 to the j. Okay. What does that mean? So, we are assuming that Ej's are bounded. Because Ej's are bounded, m star of Ej will be finite, right, because Ej are bounded, because Ej bounded implies Ej is contained in some cube, right, some cube, and that has finite measure by monotonicity and so on. We have, so finite bounded sets will have finite measure, finite outer measure. So, this tells me, so from here we get m star of Ej, well, let us write this as m star of Ej minus Fj union Fj, right. I can throw out Fj and then take the union. They are disjoint sets now, but by subadditivity I know that this is less than or equal to m star of Ej minus Fj plus m star of Fj. Okay. So, this I know is small, so that I can use. So, what do I get? I get that because they are finite, all this cancellations or taking something to the left, right, etc. will not cause any problems. So, what we have is, so this implies that m star of Ej is less than or equal to m star of Fj plus epsilon by 2 to the j. So, remember that Fj is closed and is contained in Ej. Okay. So, Fj is closed. So, this is what we have got simply from the definition of the measurability. Okay. So, Fj's are closed and Fj's are bounded, right, because Ej are bounded. So, this implies that Fj are compact. Okay. Not just that, Fj are disjoint, Fj are also disjoint. Why? Because Ej are disjoint and Fj's are contained in Ej, right. Ej are disjoint and so Fj are also disjoint. Okay. So, I have disjoint compact sets. So, their distance will be positive. So, because of that, if I take any two of them, this distance will be positive if j is not equal to k. Okay. And whenever you have distance positive, you know that outer measure adds up. Okay. So, we will use that. So, consider, so let or look at m of E, which is what we want to compute. M of E, well, of course, this is by definition is m star of E, because E is measurable. E is the, well, what is E? E is the countable union of Ej. So, maybe I did not mention that. So, let me, did I mention? No, I did not mention this. So, let us look at E equal to union Ej, okay, j equal to 1 to infinity, and we are trying to compute m of E. M of E is, so Ej are disjoint, remember that as well, and that is what gives Fj are also disjoint, right. So, m of E equal to m star of E by definition, this is greater than or equal to m star of union Fj, right, j equal to 1 to n. So, some finite. Why is that? Because Fj's are contained in Ej. So, union Fj will be contained in union Ej, which is equal to E, right. So, by monotonicity, so this is simply by monotonicity, we have this, but Fj are at a distance. So, I can apply the property to get that this is actually summation j equal to 1 to n m star of Fj, right, because the distance between Fj and Fk are positive, right. So, we have that property for m star of Fj, which of course is less than or equal to, sorry, greater than or equal to, well, what do? We use this inequality So, I know that it is greater than or equal to summation j equal to 1 to n m star of E j minus epsilon by 2 to the j, right. Each of them I can replace by whatever is in the bracket, but E j are measurable. So, m star of E j is simply m of E j. So, this I write as or greater than or equal to j equal to 1 to n m of E j, and instead of taking epsilon by 2 to the j, I simply add up and get epsilon. So, epsilon is bigger than the sum of these things, and so I am subtracting a bigger quantity. So, inequality goes in the same way. So, we have what we have proved is m of E. So, that is the measure of E is greater than or equal to summation j equal to 1 to n m of E j minus epsilon. So, this is true for every n and for every epsilon positive. So, I can let n go to infinity, and so let n go to infinity and epsilon go to 0, right. Nothing will change because the inequality is absolute. There are no constants depending on n and epsilon anywhere. So, to get m of E greater than or equal to summation j equal to 1 to infinity m of E j, right. So, we by subadditivity we already have the other inequality. Subadditivity we already have m of E less than or equal to summation j equal to 1 to infinity m of E j, right. So, since we have this and this, we get equality. So, m of E is nothing but summation j equal to 1 to infinity m of E j. So, that is countable additivity, okay. But we assume something. So, let us go back to the statement in the proof. First, assume that E j are bounded. So, we assume that E j are bounded. We need to show that without that assumption we can still get countable additivity. So, that is the next case. So, case B, general case. So, that means not assuming that E j are bounded. So, what do? Well, we make them bounded by intersecting with bounded sets. So, write Rn to be union Qk, k equal to 1 to infinity. You can choose any appropriate bounded sets, measurable bounded set, but that is not important here. Qk cubes, and let us say Qk is contained in Qk plus 1 for every k. Okay. What am I doing? So, if this is your Rn, you start with Q1 like this, okay, and then make something bigger than that, that is your Q2, and then make something even bigger than that, and so on and so forth until you fill up Rn. So, you will get Q3 and things like that. Okay. So, this can be done. All right. Well, what is the advantage of writing Qk like that? That is because, well, write S1 equal to Q1, S2 equal to, or Sk in general, Sk equal to Qk minus Qk minus 1, okay, k greater than or equal to 2. Okay. So, in the picture, well, I have Q1 is equal to S1 and whatever is here, right, whatever is here, that is your Q2 or Q2 minus Q1, that is S2, okay, and whatever will be here, that part is Q3 minus Q2. So, that is S3 and so on and so forth. So, well, so from the picture itself it is clear that they are disjoint, right. So, we will use that. So, Sk are disjoint. So, clearly Sk are disjoint. Okay. So, then we can write each set Ej. So, remember now we are in the general case, Ej are not assumed to be bounded. Okay. So, we are not assuming that they are bounded. So, these are general measurable set Ej, but they are disjoint. Okay. So, I can write Ej as summation k equal to 1 to infinity Ej intersected with Sk, right, and this would be a disjoint union. Well, this is a disjoint union because Sk are disjoint, right, and I am intersecting with Sk. So, whatever I get also will be a disjoint union. But why do I get equality? That is because if I look at union Sk, that is all of Rn, okay, because we started with union Qk which is Rn, and then we disjointified them, right. So, you get first you get this portion, then you get this, then you get the green portion and so on. So, you get Rn by taking the union. So, this is a disjoint union. Well, it is not just disjoint, Sk are bounded, right. So, Sk are bounded. So, these are bounded sets and measurable. Well, why are they measurable? Because Ej is measurable. Okay, so, let us see why. Ej is measurable and Sk, what is Sk? Sk is Qk intersected with Qk minus 1 complement, and so that is also measurable because each of them is measurable, right. Qk is a cube, so it is measurable, and Qk minus 1 complement is measurable because it is a complement of a measurable set, and this is a sigma algebra. And when you intersect two measurable sets, you will get a measurable set, right, because you are still in the sigma algebra. So, these are bounded sets and they are inside Lebesgue sigma algebra. So, by case A, well, what is A? If you assume that you have a countable disjoint union, okay, so assume that you have bounded sets disjoint, then you have proved that they add up, right, the measure adds up. So, we can apply this case to whatever we are doing now, right. So, we have written Ej as union of bounded disjoint sets. So, by that case M of Ej, that is the measure of Ej, Lebesgue measure of Ej, is equal to summation k equal to 1 to infinity measure of Ej intersection Sk, right, that is what we have. Okay. Now, using this, so use this to get union Ej. So, remember this is my E, right. I can write E also in the same manner. Well, I know how to intersect Ej's with Sk and get Ej, and then you take another union. So, j equal to 1 to infinity in the union k equal to 1 to infinity Ej intersection Sk, that is also fine, you will get E, and these are all bounded, again bounded measurable sets. So, again use A to get measure of E. Now, instead of Ej I take measure of E. I am writing E as union of bounded measurable sets disjoint, right. So, this is still a disjoint bounded measurable sets. So, measure of E just by the case we have proved is the sum of them, measure of the sum of components, right. So, k equal to 1 to infinity measure of Ej intersection Sk, we just proved this. But now you can apply whatever we have just seen, that is M of Ej is the sum with respect to k. So, if I look at this portion, this is simply M of Ej. So, what we have just proved is summation j equal to 1 to infinity M of Ej, which is the countable additivity, right. So, M of E equal to M of Ej. Okay, so, that finishes the proof. Okay. Okay. Hence, Lebesgue measure is, so hence M is countably additive, countably additive. Okay. So what? So this sort of completes the construction of. So let me state this. This completes the construction of Lebesgue measure. The construction of Lebesgue measure. Lebesgue measure on Rn. Okay. So what we have is, if you look at the triple Rn, the Lebesgue sigma algebra and the measure M, right. So this is my triple, this is the measure space. Okay. So if you recall, we started with abstract measure theory, where we had a space X, we had a sigma algebra of subsets of X and a measure mu, right. So this was the triple we had, this is the measure space, and we had various theorems, right. All those theorems will be applicable. So all the abstract measure theory theorems will be applicable for this triple as well. So let's use that to compute the Lebesgue measure of something. So there are several things to be done. We will look at finer properties and all that later on, but let's ask some simple questions and then see how the theorems we proved in the abstract settings can be used to prove theorems in this concrete case. So let us look at R2, okay, as a simple example. R2, we look at the real line like this. Okay. We also have the real line, so that is dimension 1. What is the measure of the real line in dimension 1? When I look at the Lebesgue measure of the real line, I will get infinity, right, because you can take the intervals minus n to n, that is, those are the closed cubes, right, in R1, and measure of those intervals minus n to n, this is 2n, and that goes to infinity, and measure of the real line is of course greater than or equal to measure of these intervals by monotonicity, and so this goes to infinity, right. So it is an infinite measure space. But let us look at R2. Now I am looking at two dimensional Lebesgue measure, and look at the real line here. Well, how do I see the real line? So the real line will be identified with R cross 0, right. So this is all those points x comma 0 where x belongs to R. Okay. Question. So question is, what is the Lebesgue measure of R cross 0? Okay. So when I say Lebesgue measure, this is the two dimensional Lebesgue measure, right. I am looking at the Lebesgue measure in R2. In R there is a Lebesgue measure, in R2 there is a Lebesgue measure, right. In all Rn we have constructed the Lebesgue measure. Well, how will I compute this? First of all, I need to know if it is measurable. Okay. So firstly, R cross 0, if I look at, this is a closed set, So R cross 0 is measurable. Right, all closed sets are measurable, right, all open sets are measurable, all closed sets are measurable. Okay. Now I want to compute the two dimensional Lebesgue measure of the real line. Well, what we do is, we look at whatever we did earlier. So look at interval from minus n to n inside R2. So let us call that An, the set An is minus n to n cross 0, right. This is a cube with side length 0, but let us not worry too much about it. This is also, this is a closed set, so this belongs to L of R2. Okay. How do I compute its measure? Well, that is easy. So, what you do is you can look at a small rectangle like this, right. So, let us say the side length is 1 by k, right, k equal to 1, 2, 3, etc. As k, so that set, so we have to denote that set by something. So, let us say a and k. A and k is, of course, in the x axis it is minus n to n, and in the y axis I take the interval minus 1 by 2k to 1 by 2k. Okay, I can take anything which goes to 0, it does not really matter, but let us take this. What is the, so this is also measurable because it is a closed set. Okay. Well, what is the advantage? I know that a and k as sets will converge to, so it actually converges. So, these are decreasing sets. When k becomes bigger and bigger, this becomes smaller, and k decreases to a n, okay. And measure of a and k, they are all finite, right, because they are cubes, okay. So, we can apply the theorem, right. So, recall the theorem, recall a n decreases to a, then mu of a n will decrease to mu of a, right. Whenever you have a measure, this happens, provided one of them is finite, provided mu of a1 is finite. Okay. So, apply that, this would imply that m of a n equal to limit of m of a n k, but m of a n k I know because this is a cube, right. So, it is the area is simply 1 by k times 2n, right, and that goes to 0 as k goes to infinity. So, m of a n is 0 for every n, and a n's increase to r cross 0. So, we apply the theorem again. So, m of a n will also increase to m of r cross 0, and so we get this is 0. So, r cross 0 has measure 0 in R2. Okay, so so let us stop here. We have completed the construction of the Lebesgue measure, and I have just shown you an example to compute the Lebesgue measure of the real line in R2. You can look at other lines, for example, the y axis or some curves, some other lines, all those will have measure 0 because there is no area, right. So, such things you should compute to get a hang of Lebesgue measure in higher dimensions. Okay.